Good day, everyone, and welcome. Today we have the privilege of speaking with Dr. Pierre Agostini, a Nobel laureate and a leading figure in atosecond physics, whose pioneering work has opened a new window into the ultrafast dynamics of matter. As a recipient of numerous awards and honors, Dr. Agostini has profoundly deepened our understanding of the universe on the shortest timescales imaginable, or just so far imaginable. We will talk about that later as well. His research has set the stage for new advancements in both fundamental science and practical applications. Dear Pierre, thank you so much for being with us. It's a great pleasure for our community, and we really appreciate this.
My pleasure.
So, as I already mentioned on the fundamental science, I'm really curious about your research in the physics of time and light has opened new doors to our understanding of fundamental science, right? So, how do you see the role of fundamental science in today's world where there is increasingly more emphasis on applied research and immediate results, let's say?
Right. My opinion is that without fundamental research, there are no applications. And you better do fundamental research first if you want to have any applications at all. When I look at my own, trajectory towards this 2001 experiment on atosecond physics, it looks really like a random walk. And there are a few, stages of fundamental research which had nothing to do with atosecond physics, really. And it's sort of a nice accident that eventually it turned out to be useful.
Right. Yeah, it's really amazing because before we just were thinking that the end point, like to study something on a femtosecond time scale, and now it's like even 1,000 more different time scales.
Shorter.
It's really shorter. It's really amazing. Good. And let's say with the advancement of technology and the expanding boundaries of physics and other sciences, like also complex ethical questions inevitably can arise. So which of these ethical dilemmas do you believe are most pressing today, and how should the scientific community address them? How do you think?
Well, I don't know if there are so many ethical problems on this time scale of atosecond.
Yeah, it's very short.
It's very short. I'm not sure I can answer that question really. The ethical problem. There are ethical problems, of course, and there are ethical problems in science as anywhere else. But, well, I suppose for just this atosecond business, it's not so much the ethical problem that's important. But it was more, practical and technical and stuff like that.
Okay, it's really great to understand that there are no ethical problems here at all as well. So yeah, it's really good that it doesn't relate to this area as well. If to talking, let's say, about interdisciplinary research, your work exemplifies a synthesis of fundamental physics with a cutting-edge technology to apply this? And in which areas do you think interdisciplinary research might lead to the most significant breakthroughs in the nearest future? Maybe that could be, I don't know, cybernetics, robotics, gene medicine, quantum physics, maybe other areas.
Right. I'm not sure about quantum physics. This is a question I've been thinking a lot about it, but for the moment, I don't see the connection with quantum. I mean, except that, of course, a lot of applications are in atomic physics, and atomic physics is essentially quantum. But it's quantum in the ordinary sense, I think. And well, actually, you were talking about femtosecond a moment ago, and it's kind of interesting to notice that the experiment that was in 2001 was at the source of atosecond physics is actually not very different from the same problem in femtosecond. Okay, it's just that we had to solve a problem of wavelengths and things like that. But yeah, it was essentially, yeah, at least similar to the frog method of Delgado
right.
Yeah, and yeah, so frog and rabbit are close to each other.
The names are very
yeah.
right. I see. So,
I forgot now what we were talking about when I started that.
Yeah, actually, yes. I mean about to your opinion, the significant breakthroughs in the nearest future, what could be the most, the priority fields of research?
Okay, it seems to me that one of the applications that has a lot of future in it and is the question of charge migration in large molecules. We are not doing that at Ohio State, but a lot of people are doing that now. And so if you extract one electron at one end of big molecule, then the whole density will sort of migrate across the molecule, and it will take some time to do that. And now there are several experiments that are able to measure the time, which is, of course, in the attosecond time scale. And I think that's one of most beautiful applications I see at the moment.
More and more incredible researches we will see in future, right? It's just probably it's just a beginning right now. Great.
That's right. Although it started a long time ago, 10 years ago, about.
Yes.
And it's still going on now.
That's an amazing time.
Yeah.
Okay, Pierre. And your work was like, let's say, alongside the contributions of Anne Lullier and Ferenc Krauss, and like independently led to significant breakthroughs in your field. And however, despite the independent nature of your research, were the moments when your paths crossed with Anne Lullier and Ferenc Krauss? I mean, whether through publications or scientific conferences or personal interactions, how did you exchange of ideas and results? And how did the exchange influence the development of your own research and contribute to shaping the field of attosecond science as in whole?
Okay. there are two persons there. I'm really on one side, and Ferenc Karls on the other side. With Anne, I mean, we were together at Saclay for a long time. When she started working on high harmonics, I was there. And so I remember a lot of conversations and so on. With Ferenc, it's a little bit different. I mean, I never worked directly with him. And now I heard from him that his group is working on medical applications of high harmonics and atosecond physics. With Anne, we have shared, I think, the basic ideas from the beginning, and how she observed the first time harmonics and did not expect it at all.
In
Saclay,
They started in 1970s, something, right? It was.
I was there from the 70s, but she came there and had a PhD in 83, I guess, or something like that. And and she started working on harmonics. I think the first paper on harmonics is 87. So we were together in the same group, and she was working on photons, and I was working on electrons. But I mean, we had similar problems, and we were working with similar lasers, also picosecond lasers, very long lasers at the time. So with Anne, we share all the basic ideas. With Ferenc, it's more mysterious. I mean, how did he went from the atosecond single isolated atosecond pulse that is created also in 2001 until this application now, which is more on medical problems, right? And detection of cancers and so on. So it's a little bit mysterious to me. And I asked them after I heard this talk at Stockholm in December, what the hell are you doing? I mean, is there any paper on that? So he sent me a number of papers, and I started reading that. But yeah, it's beautiful, but it's a little bit far from our own kind of thinking with Anne, where we are thinking mostly on on atomic physics and things like that. So I'm sure. I mean, he says his research is still at the stage of hopes rather than result, but he has already a number of results, and I'm sure he will make it. I mean, Ferenc is such very successful guy that he will do it.
Promising, right?
But still, I mean, it's a little bit far from the way we are thinking. I mean, medical application is, I think, is not so much for us because for Anne and me, because
in any case, it's really great that this research is so much diverse that it covers really different fields of knowledge, and it's really promising, like in medicine as well and in other fields. Great. Thank you for sharing. It's really So I would like to ask you about your personal perception of time. Like attosecond is 1 times to the power of minus 18 of a second. It's
Yeah.
something unbelievable, actually. We can observe and control electronic dynamics in atoms and molecules with unprecedented precision. And you have spent much of your career exploring the nature of time at the quantum level, right? So, has this work altered your personal perception of time and your place in the world? How do you think?
My answer is no.
No.
uh, you know, I can count to three, and then it will be 3 billion of billions of attoseconds during that time. And yeah, it's not something that you can feel as a human being, I think. Uh, it's really much too short. You have to be an electron to be to really to be sensitive to that kind of things.
Yeah.
Actually, well, it's interesting perhaps that we are already at the verge of zeptosecond. Although the shortest pulse, light pulse that we have now is 43 attosecond, but the shortest time which has been measured is another factor of 10 shorter. It's 247 zeptosecond. And
Wow.
that's that's the time it takes for light to go between two atoms of hydrogen in a hydrogen molecule.
Okay.
And so this has been measured, and has been measured very nicely in Germany. And but I mean, there's still no pulse that short, but they can't be that far. I mean, we kind of we can imagine how we can go there.
Great. May I ask you, like, about zeptoseconds? How do you think could the scales of, let's say, even shorter period, like yoctosecond, or probably we can be closer to the concept of Planck time? Could these scales ever become accessible to experimental science? Maybe in some future.
Yeah. Unfortunately, this is a domain which is at the moment still theoretical, completely theoretical. So, I mean, if you are curious, you can look at the papers by Christoph Keitel in Heidelberg. He has a number of papers back 10 years back about how we could generate those zeptosecond and even yoctosecond pulses. And but it's still completely theoretical. And I mean, if you try to think how you could do it that experimentally, there's still no obvious answer to that. And it's probably very difficult. Anyway, nobody has tried it yet. But the question is, I mean, why not? I mean, in principle, you could. It's the same thing, right? We have a femtosecond, and now we have attosecond, and we could have zeptosecond. Just the question of, how to make them. But the light is able to do that. Is able to produce pulses that short, in principle. So I'm sure at some point we will do it. And then the question is it series infinite? and it's not. In theory, it's not. There is the so-called Planck time, which is a limit where that you cannot go beyond, and the Planck time is still so far. It's 10 minus 43 atosecond. So there is still you can think of time as being infinitely divisible until it shows it's not. Okay.
Wow. It's amazing. Actually, the world, let's say, like a dual one, because from one side we have a time scale which is unbelievably short, and from another part we have some, let's say, processes which needs thousands of years, something like that, or millions of years, like in some astronomical measures. I mean, so it's all really amazing.
Yeah.
Absolutely.
Yeah, but okay, but those are different phenomena and different ways to look at them, and so yeah, you could try to stretch the scale from I don't know, from billion of years to billions of a second,
Right.
but I don't think it would help you thinking really.
Yeah. In any case, every practical part starts from a theoretical one. Okay. About some other current technologies, like, let's say, artificial intelligence, it has already led to remarkable breakthroughs in science, such as the accelerated discovery of, as well in medicine, like new drugs through, there was a research of protein structure prediction. It was by the project of, if I'm not mistaken, Google DeepMind, and it's called Isomorphic Labs. The name is AlphaFold. Then the researchers in more accurate climate models, and also in astrophysics is the discovery of new exoplanets in astronomy. So, given the rapid pace at which AI is developing, what do you think about this advancement happening in such large steps? Do you believe these processes could potentially harm the overall development of science or not?
Good question. No, I don't think it would harm anything. And hopefully it will help discovering things like the examples we were talking about a moment ago. Anything like artificial intelligence is great. I think I was a little bit skeptical at the beginning for the reason that the way artificial intelligence works, it needs to go over everything which has been done already. And from there, draw some conclusion. And so I was, thinking, how could this, invent anything? But apparently, in problems like finding new molecules or stuff like that, it can do it. It can do it. So, okay, let's hope for the best.
Yeah, let's hope. I believe that it can just speed up the processes and the parts of the experiment in different fields, and it's good in any case if it can do something just faster. But from another side, I'd like to ask you, how do you think if to say that in the future AI could make scientific discoveries independently of human input, or will human intellect always be an essential component in this process? How do you think of that?
I don't know really what to think about that. I don't. Well,
Well, I mean, just let's say if AI can work independently, could there be a situation where it makes a discovery independently just of a human being? We don't know.
yeah, yeah. I was listening the other day, YouTube stuff by Darren Stow,
Mhm.
who was talking about how how AI can invent or can help mathematicians, and
Mhm.
yeah, that he seemed to be optimistic about that. So yeah, the problem with AI is that it has been used often uh, to deceive people and to yeah, and so they could be bad utilization or bad uses of AI. But after all, yeah, atomic bomb is a bad utilization of physics.
Yes, right. A good technology, but a bad one.
Yeah.
That's right. Okay, I see. Thank you. So, let's talk about kind of motivation and inspiration. Can you say, please, Pierre, what has inspired you throughout your scientific career? What the moments when you doubted your chosen path, and how did you overcome such periods if they happened?
Yeah. This question was asked several times, one way or another. Uh, oh, one simple way to put it is, how do you choose your results?
Mhm.
And it's okay. You choose your results first. Well, if you are an experimentalist like I am, uh, you choose your results because you have, well, you have the ways to look at it, look at experimentally, and that is not always obvious. Uh, and the ideas that are behind sometimes are obvious and sometimes they are not. And yeah, if I take the example of the atosecond experiment,
Mhm.
uh, actually we had a theoretical paper, but we didn't think of the Trebino frog for that at that time, although
Yes.
it's very similar to frog. And
Mhm.
yeah, we tried it when we tried it the first time,
Mhm.
and that is in 2001. And we we wanted to see the oscillation that was allowing us to determine the phase of the harmonics. And unfortunately, the first results we had were terribly noisy, and we couldn't see anything like the oscillation we wanted to see. And
Okay.
in that case, okay, my student at the time, Pierre Paul, was very worried because that was his PhD that was at
Yeah.
stake. And um, yeah, it's only when we realized that, of course, the laser intensity is fluctuating, and we have to normalize it one way or the other. And when we did that, yeah, like by miracle, the
Yeah.
oscillation appeared. That was really nice.
Great.
Yeah, sometimes you do things and they didn't work at all because you have forgotten something, because one parameter is not right, or things like that. And sometimes they work very nice, and and you publish and you publish quickly. Uh,
Great.
I remember one of the first experiments I did on above threshold ionization. The first
Mhm.
experiment back in 1970 or something. And we did the experiment the first time, and it worked beautifully. And so we had a theorist with us, is dead, unfortunately now, and Nassim Rahman. And so we wrote the paper very quickly, and we submitted very quickly, and it was accepted very quickly. But okay, during that time, we tried to reproduce this research, and we could not reproduce it. I mean, we for at least for 2 months, I guess, we could not reproduce it. So that was terrible. And yeah, so I mean, how can you sleep? The paper is going to be published, and you cannot reproduce the result. Oh, God.
Well, it happens nowadays. It happens like
yeah,
the retractions. It's like
yeah. I remember also another time in LOA at the laboratory of applied optics, and the first time people tried to the self-model blocking, it worked beautifully, yeah. And then for a month, at least for a month, we could not reproduce that same thing. So I remember, I mean, it did not work. It simply did not work for a month or so. And then it worked again. It was hard to understand exactly why, but that's the way experimental physics works.
Great. In any case, finally it was great, right?
Yeah.
Good. I'd like to ask you about an education. So how do you envision the future of science education? What changes do you think are necessary in curricula and teaching methods to prepare the next generation of scientists for the challenges or for the 21st century? Maybe what kind of skills would you advise young scientists to pump up, let's say, right now in order to be always like relevant and achieve significant success over the time?
Yeah, well, I'm not exactly sure about that. When we started research, when I started research, I had a very bad background in a sense. I started research in 68, 69, and we started in multi-photon ionization. And my background in quantum physics was almost non-existent. At my time, we didn't have any quantum physics course at university. So, and so the first paper that my group leader gave me to read was a Keldysh paper, and really I did not understand the thing in that paper. So that was really hard. So now people are much more prepared, I would say. And so, but I'm sure for a young guy who will start research, he will meet problems that has not been solved, or it's not that's not research, and then you have to deal with that. I don't think there's a unique solution, and I think each person has his own or must find his own solution, I guess.
Yeah. That's right. I agree with you. Just additionally, in terms of scientific publications, how do you think it's could there be for scientists a pursuit for publish as much as possible, or just to make more, like to focus on a quality research and less publications?
Okay, that's a good question. My opinion is that you should publish when you have a result. You should publish it. Maybe it's not perfect, but at least you would help other people to work on the problem.
Yeah.
Now, I mean, the situation has been a little bit muddled by nature and all the journals that goes with nature and all, you know.
Yeah.
And everybody is trying to get something published in Nature, and you have to be rejected really to try something else. And I don't think that's such a good idea. I mean, some more or less ambitious or journals are also good to be used by physicists, and I'm not sure that looking for the publication that will make you a Nobel Prize or something is something that you should look for. Of course, when we did this experiment in 2001, we had no idea of the Nobel Prize that would eventually come with it.
It was a kind of serendipity in discovery, right?
Yeah.
Absolutely. Great. Thank you so much, dear Pierre. It has been a true privilege to explore your remarkable contributions to science. As probably you now have more time to enjoy life beyond the lab. Wish you many fulfilling moments spent with loved ones and in pursuits that bring you joy. Thank you for sharing your invaluable insights and experiences with us today. We really appreciate this, and it was great. Thank you so much.
Thank you. Thank you for your time, Alex.
Yeah.